Welcome to this explainer on magnetic particle theory. Look, if you're gearing up for your Level 2 magnetic particle testing certification, you are in exactly the right place. You can basically consider this your ultimate exam cram masterclass. Today, we're zeroing in entirely on the Level 2 theory and the very specific guidelines you absolutely need to pass. We're going to skip all the basic fluff and jump straight into the hard numbers, the exact equipment parameters, and those critical testing criteria you are absolutely guaranteed to see on test day. All right, let's get right into it. So here's our game plan to organize all the specific data you need to memorize. We're going to cover the principles of magnetism, magnetization techniques and equipment, essential lighting and specs, evaluating indications, and finally, the demagnetization process.
Let's kick things off with Section 1, Principles of Magnetism, and visualizing those invisible microforces.
To really get this, we have to start by looking at where magnetism actually comes from at a microscopic level. It's totally foundational. Think back to the classic Bohr model, with electrons orbiting a positively charged nucleus. For your exam, you have to understand that the true source of magnetism starts right there, with those electrons. Now, in most atoms, electrons occur in pairs. Because these paired electrons spin in opposite directions, their individual magnetic fields just cancel each other out, which leaves a net magnetic moment of zero. But, and this is a huge but, atoms with unpaired electrons create a net magnetic moment. It's these guys that actually react to external magnetic fields.
Because of that, you need to memorize this exact definition. Ferromagnetic material. Magnetic particle inspection strictly applies only to highly reactive ferromagnetic materials. We're talking iron, nickel, and cobalt. The entire reason this non-destructive testing method even works is because we can manipulate these specific materials to sniff out defects right at or just below the surface of a part. Basically, if it's not ferromagnetic, this method is completely useless.
You also have to keep in mind that a magnet always exhibits polarity. Magnetic lines of force run continuously from the North Pole over to the South Pole outside the magnet. And of course, remember the golden rule of magnetism. Like poles repel, while unlike poles attract. I know, it sounds like basic physics, but this is the literal mechanism we use to physically drag those iron particles right into a hidden defect. Moving on to Section 2, Magnetization Techniques and Equipment. This is all about the tools and the math. Okay, let's look at how all this theory translates to the real world, and more importantly, the exact numbers you need for your test. You are definitely going to see equipment calibration questions, so lock these into your brain right now. First up, if you're using a handheld AC yoke, that heavy U-shaped electromagnet with the articulating legs, you must perform a standard 10-pound weight lift test prior to your inspection just to verify its lifting power. And what about your digital light intensity meters? Well, strict industry standards say that light meters require calibration verification within the previous 12 months. Do not let them trick you with different timeframes on a multiple choice question. 12 months, period. All right, I need you to burn this next formula into your memory. Ampere turns equals 45,000 divided by the length over diameter ratio. What's this actually for? It's the standard empirical formula used to calculate longitudinal magnetization when you're using an encircling air core coil. So if you hit a question asking how to calculate ampere turns for a simple part inside a coil, you are looking for 45,000 divided by L over D. Now, how do you know when you've actually established a strong enough magnetic field? When you're measuring the tangential applied magnetic field strength with a Hall effect meter or Gauss meter, the absolute critical threshold you need to memorize is a minimum of 30 Gauss. That equates to 2.4 kiloamps per meter. If your field strength drops below 30 Gauss, you're risking not forming a visible indication at all. Which brings us to Section 3, Essential Lighting and Specs, Illuminating the Invisible. This domain is packed with strict numerical thresholds that you have to know cold. When you're doing fluorescent testing, the specific wavelength of your light source is heavily regulated. Your UVA LED lamps have to produce a peak wavelength exactly between 365 and 370 nanometers. They chose this very specific range because it perfectly excites the fluorescent dyes in your particles without bleeding over into harmful or just plain ineffective spectrums. Remember that super tight window? 365 to 370. But what if you're doing non-fluorescent or visible particle examinations? Your magic number here is 100. You need a minimum visible light intensity at the examination surface of 100 foot candles. This guarantees you have enough standard lighting to clearly see the contrast between your colored iron particles and the surface of the part you're testing.
On the flip side, you really need to know the absolute maximum ambient visible light allowed in your darkened area when you're doing fluorescent testing. That number is tiny, just 2-foot candles. Think about it. If you have more ambient light than that bleeding into your inspection booth, it's going to completely wash out that bright green-yellow glow of your indications, and you might miss a critical flaw. So just to recap, minimum 100 for visible, maximum 2 for fluorescent ambient.
All right, Section 4. Evaluating indications. This is how we actually identify the flaws.
So the field is applied, our lighting is meticulously set to code, and now we have to interpret what the magnetic particles are trying to tell us. Theoretically, a break in the material creates brand new north and south poles right at the defect. This forces magnetic flux lines to exit the metal and form what we call a leakage field. In reality, that leakage field acts like a localized magnet. It physically traps those microscopic iron particles, forming a stark, highly visible line right over the crack. It's pretty amazing when you think about it.
You are completely guaranteed to be tested on the 3 categories of indications. First, relevant indications. This is what we're actually hunting for, leakage fields caused by actual defects like cracks or seams. Next, non-relevant indications. These are still caused by real magnetic leakage fields, but they're created by intentional geometric features that don't need evaluation, like a threaded area or a keyway. And finally, false indications. These have absolutely nothing to do with magnetic forces. They're just particles that got mechanically trapped by gravity, a rough surface, or some rust. You have to know the difference between non-relevant and false.
Make sure you highlight these next metrics in your study notes because they show up constantly on tests. When you're checking your bath concentration using a pear-shaped centrifuge settling tube, wet fluorescent particles require a settling volume of 0.1 to 0.4 milliliters per 100 milliliters of vehicle. But wet visible particles require a significantly heavier concentration, 1.2 to 2.4 milliliters per 100 milliliters. That is a massive difference, so keep those specific ranges firmly tied to their respective methods in your head.
Let's wrap up with Section 5, the demagnetization process, or resetting the metal.
Okay, we found the flaw, but our job isn't quite done yet. This final exam domain covers the very last step, resetting the metals so the part can safely go back into service without attracting random tramp metal or messing up moving parts. Usually, we just pass the part through a reversing and stepping down AC coil and call it a day, but you need to know the exceptions. If a part has an extreme size, a really unusual shape, or super high retentivity that makes standard demag impossible, you can use special alternative techniques listed in the guidelines. Be ready to spot these terms on a multiple choice list: rubber mallet demagnetization, demagnetization by positioning, and transient demagnetization. And finally, no matter what equipment you end up using, the core theoretical procedure for demagnetization always relies on one exact sequence. Step 1, you have to subject the part to a field equal to or greater than the original magnetizing field. Step 2, you continuously reverse the field direction. And step 3, you gradually decrease that field all the way to 0. This stepping down action slowly collapses the aligned magnetic domains, forcing them back into a randomized, totally neutral state. Good luck with your studies, everyone. As you sit down for your exam, I want you to remember this. Mastering these exact numbers, the 10-pound yoke tests, the 30 Gauss minimums, the specific fluorescent wavelengths, it isn't just about passing a test to get a piece of paper. It's about translating theoretical perfection into real-world vigilance. If you hold yourself to these strict numerical standards, you are going to be the technician who spots that microscopic fatigue crack that literally saves a pipeline, an aircraft, or a bridge. So, how will you use this knowledge to ensure the structural integrity of the world around us? You've got this.